Welcome to the study of electric force. We will be looking at the law of electrostatics and Coulomb's law in this section. The law of electrostatics is a basic statement that charges come in positive and negative signs, and that the law is that like charges repel and unlike charges attract. So this is a force law that will have two directions associated with it. Toward or away from the charges. The force law in particular is expressed by Coulomb's law. Coulomb's law is somewhat like the gravitational force law with respect to the relationship between the property of charge and then the distance between the charges. The force law expresses for us the inverse relationship. The force law depends upon the sign of the charges. Q1 and Q2 are the symbols for the charges. They can be plus or minus. The law of electrostatics tells you what the direction of the force is. Coulomb's law tells you the size of that force. So if Q1 is our focus, we ask the question, what is the force Q1 feels? Then we calculate K Q1, Q2 over R squared, and then recognizing that if Q1 is the same charge as Q2, then it will be pushed away from Q2, or if Q1 is the opposite charge to Q2, then Q1 will be attracted towards Q2. So this is a force law that we have to bear in mind, that there's direction as well as magnitude. It truly is a vector relationship. As you can see, it's an inverse square law, which means that as the distance doubles, the force diminishes by twice the doubling distance. It's linear dependence on charge in the numerator. The constant K is expressed as 9 times 10 to the 9th Newton meter squared per Coulomb squared. The constant K is also related to a fundamental quantity called the permittivity of space, where epsilon 0 is the permittivity of free space, defined as a vacuum. And then the relationship between epsilon 0 and epsilon is called the dielectric constant. And that expresses for us the degree to which the material that is experiencing this electric field can be polarized. That is, the charges can be sort of lined up against or with the electric field that's being imposed upon them. So our primary goal with using Coulomb's law is to determine the force, the electric force, that a charge is experiencing due to the presence of a second force. So let's take a look at this example. We have two charges separated by 0.20 meters, which is 20 centimeters. And the one charge, which we've labeled Q1, is 4 microcoulombs. A microcoulomb is 10 to the minus 6, so this is 4 times 10 to the minus 6 coulombs. And the other charge has a value of minus 4 microcoulombs, so minus 4 times 10 to the minus 6 coulombs. So you notice that the question being asked is to determine the electric force on Q1 due to Q2. So we're going to use Coulomb's law, K Q1 Q2 over R squared. R is the distance between the two charges, and we're dealing with point charges here, so it doesn't matter how large the charge is, it's treated as a point. So K is 9 times 10 to the 9th, and then the Q's are in microcoulombs, so when you multiply 10 to the minus 6 times 10 to the minus 6, you'll get 10 to the minus 12, and then 4 times 4 is 16. So you've got a 9 times 10 to the 9th, you've got 16, 10 to the minus 12, right? And then we're going to divide that by 0.2 squared. 0.2 squared, right? So that's going to be like multiplying by 25. So I'll leave that calculation to you to finish up. And then we'll take a look at an additional problem here. What if we have three charges? And here we have all 4 microcoulomb charges. 2 of them are positive, 1 of them is negative, at the corners of a triangle whose sides are 0.1 meters apart. Remember that the force law is between pairs of particles. So you will have, if we labeled them from top or clockwise, we'd have 1, 2, 3. The force between 1 and 2, the force between 2 and 3, the force between 3 and 1. So we'd have 3 calculations to do here in order to determine the force in the case of this equilateral triangle. In this case, we have a charge of 4 charges located at the corners of a square whose sides are a ½ meter long. And it's looking from the top left corner and moving clockwise. All these charges are expressed for you. And we want to know, what is the electric force on the top left charge due to the others? So the top left charge is kind of like our Q1, and the others are 2, 3, and 4. And we will calculate the force experienced on Q1 due to Q2, on Q1 due to Q3, and on Q1 due to Q4. Now those will all have different directions involved because some of the forces are plus, some are repulsive, some are attractive, based on the size of the charges and the sign of the charges, that is. So this problem's a little bit more complicated because we're going to have to calculate the magnitude of the force between each of these pairs, and then determine the vector direction, and then add up the vector components in their x and y directions, and get a final vector magnitude, which would be the answer to this particular problem. So that's the extent of the Coulomb's law in terms of electric force. Now, we want to think about this. The electric force expresses for you the force between a pair of particles. And depending on which particle you're asking for the force on, then you either, if you're asking for what's the force on particle 1 due to 2, or particle 2 due to 1, you have a different vector direction involved. But that's fairly straightforward to calculate the magnitude and then the direction and do your vector algebra. Now the question remains is this: what if particle 1 was not there at the location, but particle 2 was still, charge 2 was still present? Is there something that exists at the location of particle 1 even though particle 1's not there? Because just because particle 1 is there means that that's where a force acts on particle 1. But was there something there to begin with as a result of particle 2? And so that's what we call the electric field. The electric field is produced by charged particles, and it has 2 directions, away from positives and toward negatives. The electric field is calculated by the force between the 2 particles divided by the particle experiencing that force. In other words, if Q1 was the particle we wanted to know what its force was, then the force law would be KQ1 over KQ1 Q2 over R squared. And then if we wanted to know the electric field, we would divide by Q1 so that we had an expression just in terms of particle 2. It would be KQ2 over R squared. And what that is saying is the electric field at the location R, due to the presence of Q2 at a distance away, R away from this point, is given by the force divided by Q1. Here we see this calculation. Notice it says E1 is the force experienced by particle 2 divided by the charge Q2, which eliminates the charge Q2 from the equation and tells us the electric field produced by Q1 at the location of our Q. So here's an example. What is the electric field 0.2 meters from a 4 minus? So we see we have a 4 microcoulomb charge, 0.2 meters from a location of interest, and a constant 9 times 10 to the ninth. And as a result of that, we get a rather large electric field, 900,000 newtons per coulomb, and it's pointed away from the location of Q1, because Q1 was a positive charge, so its electric field is away from it.